Thank you very much for the kind introduction, Peter, and thank you very much for inviting me to present some of our work. And I do apologize that I cannot be with you in person, but hopefully in the years to come, it will probably get easier. So I really, as you said, I would like to take the conversation forward that Max Riegel left with us in a question: why do we need LiFi, and why is it not, or is it better than, okay, how can it be better than RF, and what do we need to do to make it better? And there's one thing that allows us to do better than radio, is because the spectrum is 3 orders of magnitude wider than the radio spectrum, but I come to that in a minute. So I would really like to start by looking at two standards, if you want, that Max Riegel also touched upon. The IEEE standard here that you see in blue over the last years, and also the cellular standard. And what you've noticed, what we can see, is that the data rates through all the generations, all the versions of standards, has increased exponentially, because the data rates on the y-axis is plotted in logarithmic scale. So a linear graph means exponential growth. And also the message from this graph here, and it's work by Gerhard Fettweis and Holger Poche in Munich, the goal points towards a terabit per second communication capability in both standards. In cellular, so i.e. 6G has as a key performance requirement at 1 terabit per second written into their sort of performance indicators, but also Wi-Fi. And I would like to point out one important thing here, and is that the slope of that straight line here in Wi-Fi has slowed down for the last 10 years. As you see, we have Wi-Fi 6 now, maximum data rate 10 gigabit per second. Wi-Fi 4 was already 1 gigabit per second. And I personally attribute that to the fact that there is not enough spectrum in Wi-Fi to really continue with this high data rates. As is the case in the cellular standard in red, where you see a very nice straight line, and with 5G now being sort of in the region of 1 gigabit and higher. But as you know, in cellular, there's always the World Radio Conference, this next one in next year, where a new spectrum is identified. And that basically helps growing that trajectory. That's the very important sort of point I wanted to make. And the other is that there is a killer app, and the register may be the killer app for Wi-Fi many years back, but now I believe that AR, VR, and holographic displays in the extension will be a killer app for LiFi. And I'll try to walk you through why I believe that, and show you a few examples as well. So I would like to show you sort of the mobile data traffic, and the exponential growth is shown here in the left graph. So what we have done here is we have taken the Cisco white papers that are all publicly available since 2011, and they always predicted the mobile data traffic in a horizon of 5 years forward. So we now have the benefit of hindsight, so we could check the first white paper in Cisco from 2011, in checking sort of what the real data traffic was compared to the prediction. And we've basically gone through all the white papers up until 22 and have calibrated the models with real data that was publicly available in traffic. And based on that, we've developed 2 models, a pessimistic model in the predicting the traffic going forward from now and up until 2035. And basically looked in 2 models, a pessimistic one and a realistic one. And if you take these, you see these dashed lines in red and green. So it means that the traffic will grow in the next 10 years or so between a factor of 25 and 100. So that's the growth of data rates that we can expect, or data traffic. Now before I do this, now there's another important metric, is the spectral efficiency in radio, so the bits per second per hertz. So in other words, how many bits can you squeeze into 1 hertz of bandwidth? And this is also predicted here with this right-hand graph. And what we notice is that in the optimistic case here, the spectrum efficiency increases from from 6 to maybe 20 or 24. So a factor about 4, or maximum 4, but more realistically a factor 2. So now if you compare the spectrum that is currently being used in cellular, and you see an example here in the United Kingdom of all the operators, and what that amounts to a spectrum of 500 megahertz in total, and Wi-Fi currently used about 400 megahertz, so it's about 1 gigahertz of spectrum. Now, if you multiply that with that growth of 100, but also then divide by the spectrum efficiency gain of 2, you would end up in a spectrum that is required of 57 gigahertz of bandwidth. And you may find it in the higher millimeter wave, but in terahertz communication, in terahertz spectrum in radio, there are no real devices, whereas there are plenty of devices in the optical spectrum. And also, I need to say that adding a gigahertz of spectrum, as is done in Wi-Fi in the 6 gigahertz band, really doesn't cut the mustard, if you want, if that makes sense. So now going back to the XR, AR, VR sort of mixed reality problem is very nicely sort of formulated again by Gerhard Fedweis. If you take a monitor, we would expect a resolution of 8K, which is sort of good quality to make you not seasick in an AR, VR glasses with low latency, and also gives you a very natural like visual in your screen. But typically screens have a 30-degree horizontal angle of view and a 17-degree vertical angle of view. So very narrow sort of visual field of view. That typically is the case. But if we want to have true AR, VR experience, you're looking at a 180-degree experience. So you have much broader vision, 180-degree vision. And even if you would apply a factor of 1,000 in terms of compressing the data rate, you would still require between 1 and 10 gigabit per second per stream. So imagine now a classroom environment where you have a new teaching content that are streamed to AR, VR glasses and 20 to 30 pupils in a classroom. You talk about at least easily 100 gigabit per second in that environment. And to the best of the current capability, Wi-Fi and cellular will struggle to achieve these data rates, and Wi-Fi would really drive it to the extreme capability. So we are reaching the boundaries of radio right now with those requirements. There's another example, another use case that looking at the highly dense environment, a stadium. And this is taken out of this report in the Super Bowl sort of stadia in the United States. And there's one thing that is very nicely matching with the 100 times increase in data traffic predicted forward. We can also see it backwards. Here in 2012, it was 300 gigabyte data shifted around in a stadium requirement, in a stadium environment, which is now 31 terabyte. So it is a factor of 100, interestingly. So we see in that environment as well, in that use case, the data rates increase, and the factor of 100 is perhaps quite a realistic one, rolling out to other use cases. It is currently using, in these environments, it is using Wi-Fi to deploy this high data density. And the only way, and you see this in that report, written into that report, is the only way they achieve this high density is by putting Wi-Fi boxes under the seat, because human bodies act as signal attenuator. So because of the high water content. So basically everybody sitting on that chair would basically dampen the signal power so that more of these gray boxes can be installed, and hence more capacity could be added to this environment. I personally think this is not a viable way forward in using humans and sort of the environment to ensure that interference is mitigated and higher density can be achieved. There's a better way of doing that. So that brings me to LiFi. And LiFi, I want to basically show what LiFi is. And it's LiFi networking. It's not point-to-point. It's not the IRDA use case. It is not the TV remote use case where you point towards a receiver, it is really going into this networking domain, where we first of all need to have a strong backhaul that delivers terabit per second. Yeah, that could be fiber, that could also be wireless, optical wireless. And then we have multi-user access, we have mobility. So we have one light source transmitting to multiple users in a bidirectional way. We need to allow random orientation of that smartphone. It's not basically linked always into the access point. There's interference between light cones that need to be managed. There's mobility, there's random blockage. In this case, for example, that the head of that person would block the line of sight. But as you see, there's another link opening up here. So we need to have diversity integrated, cooperative multi-point transmission. We are really talking about a networking technology, not a point-to-point technology. And that's really fundamental in Li-Fi. And the only standard across all these standards that have been presented so far is 802.11bb that allows that networking capability, because it comes from a networking sort of heritage. It is basically built upon 802.11, the Wi-Fi standard. And as Max Riegel has nicely pointed out, that the modifications required in the PHY layer are basically close to zero. And the modifications in the MAC layer are zero. And you can, and therefore, harness all the benefits of the MAC layer, such as authentication, encryption, and all the developments that are put into Wi-Fi now directly available to you if you use that standard for light communications. And the good thing is, it is maybe in operation since 2017 with a interest group, but now there's a standard being ratified as I speak, actually. And there will be hopefully a ratified standard by the end of this year and beginning of next year, which really allows the industry to build interoperable Li-Fi optical front ends that can be attached to any smartphone by utilizing existing estate in that phone with this existing baseband, existing MAC layer that Wi-Fi offers, by just converting in the case the RF signal down to baseband. That's the only thing that is needed, as Max has nicely pointed out. So that's really going into the networking here. Now I'd like to take this a little bit forward into the future, and as I said, a terabit per second is the objective, and there's been excellent work, great work by my colleague in Eindhoven, Ton Konen, that have started looking at delivering gigabits the data to users in a mobile in an indoor environment by using a very sort of relatively low complex access point. The idea they put forward is that the access point is centrally put into these boxes here, and then the access points in a room are basically getting multiple wavelengths, multiple fibers go into an access point. As you see here, all these connectors are fibers going into this access point, which is a simple device in the sense that there's no signal processing in there. It's just fibers and a special grading structure, which means that different wavelengths are sort of reflected in a different way, and that's how they can steer the beam to different users, mobile users in a room, by just switching across multiple wavelengths and thereby allowing sort of this sort of downlink capacity per wavelength. So that's a very interesting, very nice first step in building really high-speed indoor light communication networks. I also would like to show one case that we have done in partnership and in collaboration with Kyocera Solar Laser in Santa Barbara. They are revolutionizing indoor lighting by using laser light. So instead of a blue LED, a laser would pump, or would not pump, would basically excite phosphor that would create white light. But the benefit is that the emission spectrum of these laser light is very narrow and also high power and also eye safe. And that means that we can put multiple wavelengths together into one device, into one lighting device that you see here, which carries, in this case, 10 different wavelengths, but it's not switched wavelength. It's now really used to illuminate in the visible spectrum. So we use the visible light to transmit data, but also there's infrared spectrum also integrated into these devices. And we have achieved at CES, we have achieved there 105 gigabit per second by this what I call sort of future LiFi access point that also currently is these devices, and John Peake will talk more about it. They are in current cars integrated, so it would allow very high speed car-to-car communication with these devices. So that's an example of really where it takes the capability beyond what radio can do right now. So now that brings me to our own. What we are trying to achieve there is indoor networking, as similar to what Ton Konen did, but using infrared light and using different optical approach. But yeah, want to achieve multi-user capability, handover, and achieve 4 orders of magnitude higher capacity than current 5G networks. And that's really where this sits. It's a project that feeds into 6G roadmap as it's worldwide rolled out. So what we do is, again, use cases is ultra high speed communication, multi-K TV, but we use VCSELs. These are little lasers that you see here, small size. They have high bandwidth, 10 gigahertz and higher, high efficiency, and they're easy to fabricate. They are in sort of face recognition devices and in many devices already integrated into mobile devices. So our approach that I would like to lay out here is the following. So we built a structure of an array of arrays of VCSELs. So you see here a pyramid with an octagonal base, and we cup the top of it. So we get 9 planes, slightly slanted, slightly different angles. And each of these arrays, each of these dots is a VCSEL. So we have in total 225 different beams. And this is a grid of beam approach that now, for example, one beam covers an area, a cell of 40 centimeter diameter. That's the cell. That is the small cell concept that we've basically taken forward here. And we cover the entire area with 225 beams. And then only thing to shape the beam is we need a lens. We need an optical system. And here we've looked at different planar convex lenses and have selected one that gives the best compromise between coverage and range. That's an example with that lens. And then we've taken that into a complete simulation. I don't want to go in all the math, into all the equations, but I do apologize that I don't have an equation here. So that's the noise power. It is different noise sources, shot noise, thermal noise, and relative intensity noise, all taken into account. Then we build a model in order to calculate the signal to interference plus noise ratio. This term here shows that we have taken interference into account. We use a certain performance metric, which is called bit error ratio. And based on that, we've calculated the rate that we can achieve with that system. And this is something I wanted to show here. So this is the room. It's 5 by 5 meter, 25 square meter. You see these 225 beams and the signal to interference plus noise ratio here. But if I go to the right, this is the more important graph. You see the data rates that can be spatially achieved. And the peak data rate with that system is 20 gigabit per second. And the lowest data rate per cell is about 10 gigabit per second. So every cell gives at least 10 gigabit per second. Of course, we have these interference regions, which are blue. If a user is in that region, data rate would go to 0 because of interference. But I give you an example in a minute how that can be mitigated. The point really is here, we have 225 cells of at least 10 gigabit per second. So the aggregate data rate in that room would be 2.25 terabit per second. And the optical power is short of 2 watt. And we also have different power allocations to different VCSELs, different regions of the room, but all under eye safety regimes. So now the question about interference can be solved quite simply by applying different clustering approaches. So we have a scenario 1 where we've taken, for example, 25 VCSELs and defined that as a cell. So all these beams now cooperate and send the same information. We can have a different structure of how we cluster that scenario with 9 beams forming one cell. And then we can have an almost indefinite number of beam clustering methods. So if we did that, what we end up is different lines of interference. So scenario 1, for example, gives you the interference line in these 25 clusters. So if a user is in there, you would just switch to a different beam clustering scenario where an interference region such as this one suddenly becomes a high data rate region. So essentially you mitigate interference by selecting the clusters in the best, optimum way. And that's the intelligence, the machine learning and the intelligence that we will bring into that system to allow this the adaptive beam clustering. That brings me to the end of my talk, and I want to really say is we don't have to wait until terahertz devices come out there. There are optical devices right now. It's VCSELs, it's micro LEDs, it is a laser light with which we can build terabit per second wireless networks, and emphasis is on networks right now. And we've shown here an example where we've achieved an aggregate data rate of greater than 2 terabit per second with a grid of beam approach, a switched grid of beam approach. And really what I want to say is, as we're going into 6G is, I mean, there's all the generations had paradigm shifts, and I see a real paradigm shift in 5G to 6G is to move into the optical spectrum to build wireless networks with similar features as RF, but significantly improved experience. And essentially what we are up to now is really merging the advances on the data rates and the capability and latency that fiber can deliver, especially hollow core fiber, with the networking capabilities that cellular systems can provide. And that forms a sort of a radical and fundamental breakthrough in terms of delivering all the KPIs that we are needing in order to keep wireless communications future-proof. And with that, I'd like to thank you for your attention.